issues, which is a big thing. He's talking today about one of the other tasks that we are performing in ICTUSnet as part of the methodological and innovative issues that we are addressing in. And he is focusing on today on showing the guts of the process mining technique. So to discover the processes that are actually the actual care processes on stroke patients in the different regions that are part of ICTUSnet. So please, Juan, the word is yours.
Thank you very much, Enrique, for this kind of introduction. I'm going to share my slides. Let's see if that works. I have to
Not yet.
Not yet, right? So I have. Can you see them right now? I think so.
Exactly, yeah.
So I'm going full screen. Let's cross fingers that going full screen. You can still see them full screen? Great.
Full screen.
Great. Yeah, I have some animations on my slide, so I cross fingers so that these animations work. Because I've never tried animations online ever before. Anyway, so thanks for the introduction again, Enrique. And first of all, I have to say that I'm going to present this process mining work we have been developing here at the Aragon Institute for Health Sciences. And I have to thank the rest of the team because I haven't done this work by myself. So there has been Carlos, a colleague in the biocomputing unit and responsible for our data lake of clinical information, and also Paco Estupiñán and Enrique. Paco is as a epidemiologist in Enrique's team. So it has been a work from all teams and especially this four of us. Okay, so let's go ahead. This is the scenario. Okay, the incidence of stroke in Spain is high, and as you may know, I think that most of our audience have some.
Excuse me, Juan, but you haven't moved the next slide.
Sorry, you can see the next.
No, hasn't been uploaded yet.
Oh,
list.
So this is so you're still seeing the previous one?
We are seeing the first one.
So the title one.
Yeah.
And right now it has changed or something?
Not yet. Not uploaded
Not yet. Great. So what are you seeing right now? Right now, nothing?
Right now, nothing. Now our faces, you and I.
And now, scenario?
Now I start the screen sharing. So we can see that you are sharing the screen, not yet present.
Really?
Really.
Oh, God.
You can send it to me, maybe, and I can upload it for you.
Sorry, I thought that. I don't know what happened this time. Sorry for the inconvenience.
Couple of minutes of entertainment.
Yeah.
Don't worry. This is the
yeah. How's it called in English? We're having.
You are emailing me or?
Yeah, I'm.
Or chatting me or what are you doing?
Email.
Okay. Not you here.
No. Oh, what is that? They are huge.
Marta, please go ahead with something else.
I send you right now. I'm trying to
Okay, I'm not getting yet.
You cannot see them, right?
Nope.
Nothing?
No,
nothing in there.
It's black.
That's wonderful.
But
So let me,
it says double click to enter full screen. You have to double click something.
somewhere, I don't know what, because I cannot see. I see my full screen. So I thought that it should be. So let me.
So, Enrique, did you get slides?
I haven't gotten yet, though. I mean, you just why don't put it on my on Skype,
Yeah,
so I can get it from Skype.
Oh, sorry. What is that? Just sent.
I got it.
You should
Downloading it.
Yeah.
Open it.
Share them.
And in a second, change the screen.
Good.
Right.
Sharing the screen, sharing the screen, sharing the screen. Share.
Yeah, we can see the. Yeah, we can see the. Yes.
Okay.
Okay,
Nice.
great. Thanks.
So I will spend a lot of time saying next slide, next slide. So well, the scenario is that we have, at least in Spain, we have these incidents that from members of the Spanish Neurology Society, and we know that the survival of stroke will be improved by attending access. And this is why the code stroke strategy appears, okay, which is a clear pathway. Pathway means the care activities, how to proper perform the care activities so as to improve or to provide the best care for managing this ischemic stroke. So the idea for us is try to understand a little bit more the code stroke strategy. Next slide, please. The code stroke is a complex strategy. So this is just the protocol for providing fibrinolysis or surgery or no action. Okay, this is part of the overall code stroke. So imagine this trying to avoid this in the reality. Next slide, please. So the point is that in this scenario, the question that could arise and what we wonder ourselves were, how can we check the adequacy of the code stroke implementation in real life? Or how can we measure the effect of the pathway or the clinical pathway in the patient survival? There is an effect in the patient survival. So starting with these research questions, we went to the process mining methodology. So next slide, please. So what's the process mining? Process mining is an, let's say, not so new data mining set of algorithms. And the idea is to capture the whole care process. Typically, what has been done in this kind of analysis was to create this overall, let's say, indicators, okay? But our idea is to go a step beyond. So observe at fine grain how the care is delivered. How? Using these real world data sets that Enrique presented at the very beginning, okay? And if you go, let's say there is an animation in this slide. So the idea is you move to the animation, you have the data sets, they appear, they don't appear. Yeah, so we have the data set, you put your magnifying glass, instead of seeing one contact to the healthcare system as a whole, the idea is to go one step beyond, observe them in detail, and see how the whole process is given. So from the starting point, next element in the slide should be from the first contact in the care activities, like for example, the admission to the urgent care and urgent care department, till the end of the caregiving activities, for example, to the discharge, until the discharge of the hospital. Okay, so next slide, please. There is some vocab related to this process mining, and I want to clarify them because I will be using this vocabulary, and it's interesting to have a common basis. So we talk an episode as an episode referring to the whole care activities from this entry point to the exit from the system. For example, entry to the emergency room, urgent care, and being discharged from the hospital. That should be the whole hospital, the whole episode. Sorry. What's an event? An event is a portion of the whole episode that refers to a given care setting. For example, in our case, I will keep talking about that. We have events related to urgent care activities, events related to hospitalization activities. What are the activities? Activities are the core elements in this process mining and refer to care elements, caregiving elements, which have a timestamp associated to it. Okay, for example, the admission to the emergency room, okay, will have the timestamp where that occurred in the real life. The same for the discharge, the same for example, the fibrinolysis a patient could have been treated with. That's the core element. Remember that timestamp elements, timestamp events are the activity. Timestamp elements of the caregiving episode are the activities. Then we have some attributes. Attributes are details, are characteristics of the activities or events. For example, you can have the attribute of an event related to the hospital where this event happened, where this emergency room was located. Or you can have an attribute related to an activity, which relates, for example, to the medical doctor which performed this specific activity. For example, that push or punch the patient with the fibrinolysis treatment. And at the very end, we have the log and the activity log, which is the sequence of the overall activities, okay, within an episode that a patient suffered, okay, which is the detail of the timestamp elements that took place in a caregiving activity from the very beginning to the very end of the episode. So next slide, please. So what is the methodological approach? Next one. So the methodological approach to perform this process mining consists of this set of events, this list of steps, and steps, activities. So the list of steps. So the first of all, we have to design a common data model. Then we have to map this data model with the real world data sources, specifically design the case, define the case and how to extract the data to put all the data to at place to then link the events, generate an activity log, and discover the effective processes that have took place in the reality, and then evaluate the results to answer our research questions. So thanks. Good one. So what's this data, this common data model or data model? A common data model, it's or a data model in general, it's a abstraction of the how you can organize the data in with a semantic consideration. So the data is spread across the systems, but so as to solve your specific questions, you have to organize them in a manner that has some a semantic on it. So what have we put here? So this is a nomenclature we use in computer science, where we divide the different concepts in different structures. Here, what we have is an episode. Okay, this box is an episode. The episodes have attributes here, the episode ID, when it starts, when it ends. An episode is composed by a series of events. Okay, the events have identification, when it starts, when it ends, an order. An event could be different types, could be an urgent care event, an hospital event, an event took place in a healthcare facility. So this is an organization of the whole knowledge in a structured way. Okay, what you have using this will serve to properly develop the rest of the elements to solve to perform the process mining. But you have what the very first thing you have to do is to fill this common data model. Please, next slide. With the real world data sets. So how can you fill that? But what you have to do first is to map this data model with your own real world data sets. Okay, look at your information systems, in your healthcare systems or your healthcare data providers, wherever you are able to access data, so as to map these concepts with the real data. Here in Aragon, we're able to map the urgent care events from our urgent care information system, which is called PCH Urgencias. And we were able to map the hospitalizations, both the acute hospitalization and the longest stay hospitalization, using the CMDPD, which is the minimum data set which is provided at in hospital discharge. It's a kind of claims data. So next, once you have your common data model, you have to specifically define the case. So which is the people which are the people who are the people you are going to analyze. In that case, the case definition is very simple. So it's just patients with a stroke suspect in a time frame. We were working in the original analysis was from 2017, the year 2017, but the very basic definition is patients with a stroke suspect. What the reality is that this very simple definition results on a very complex way to extract data. Okay, so next slide. I don't go into the details, but basically you have to go through the information systems, in that case, the urgent care, hospitalizations, check the diagnosis which have been provided by neurologists, and then cross the patients so as to properly detect the events in these information systems, then cross the detected patients with the patient's database. So it has some complexity, and in fact it results in, if you go to the next slide, it results in three SQL queries, because all of this information was stored in a SQL database. So 3 SQL queries with nested selections, which is somehow, you can, there's an animation here. There is this complex queries, so as to extract the effective data, to map them into the common data model, and then start working in the process mining methodology. Well, first in the linking, in the part of the linking pre-process mining methodology. So with this, what I wanted to admit is that once you have this common data model, you have to feed them, and feeding them, it's a complex element and a very critical one. Okay, because you have to go source by source, do this map, and then properly extract the data. So that's one of the key points, the data structure. So case definition, common data model, case definition, data structure. So if you go to the next slide, so once you have this information, basically what we will have at this point is the events you have extracted from these information systems. We have to link the events, because sometimes you can have these events already linked, but in general, what we have observed is that the different healthcare facilities, different healthcare organizations don't have the events purely integrated to represent a whole episode. So what we want to see is the caregiving continuum. So we want to be able to link from the very entry point to the very exit point in the code stroke pathway activities. So what is this event linking? Is once you have the different events, be able to consider a set of them for a given patient a whole episode. a single episode. All of them are related and represent a single episode. So next slide. So what we do? So once we have all events for all patients in a huge data set, which is what we have obtained from these SQL extractions, what we do is, first of all, is sort all the events, considering the time of concurrence and the patient who was involved in the specific event. Then we compare events incrementally pairwise, and we perform two type of linking. This is the key element in this linking procedure. We compare, for example, one event of urgent care and another event the following once we have been sorted of the hospitalization, and so as to link into a single episode, it has to follow a logical linking rule which states that the discharge type, for example, in the urgent care should be coherent to the admission time in the following event. For example, if the urgent care states that the discharge was at home, the following one couldn't be admission to an hospital, to the hospital, because it is not a logical, it does not follow a logical linking. The same for chronological linking. The discharge time and admission times should follow some coherent time. It couldn't be so separated or overlapping. We have, during this linking procedure, we detected a lot of inconsistencies because sometimes the times wasn't properly introduced. Sometimes are automatic, some other times are manually introduced, and that this manual introduction is sometimes error prone, and we were able to capture these errors and sometimes solve them, and instead of having these errors, be able to detect whole episodes. Okay, so what we have right now, we sort all the data. Okay, we have data for the patients from different events, different venues, from hospitals, urgent care, etc. And right now, after applying this linking procedure, we have episodes per patient related to cold stroke for just the cold stroke care pathway. So we store them in a documental database in one of these MongoDBs. It's next slide. And we have a kind of patient history. Okay, this is what we have. A document storage is, instead of having these columns, the regular storage columns and variables and patients, etc. What we have is documents, which is a more complex, a little bit more complex organization where the different elements could have different variables. Okay, and that's easier to manage when there is no a fixed structure. Okay, this type of storage is to manage structured information with some variability in it. What we store here, we store somehow the patient history of a stroke episode. So if you go through the animation, you can see that we can store with different places where the patient has been living. This is the location history, we call the different addresses where a patient has been living. And also the next one is the episode list. So is for every single episode, the details, the inner details of all events, the urgent care events that compose the episode, and also if you go move forward, in that case, you can see here is the first one is the emergency room events, which precede the hospitalization event. Okay, and that conforms. Okay, the patient history, because you can have more episodes for a single patient. Okay, and now we have this kind of patient history. And then next slide, please. What we do is transform this history into an activity log. What's the activity log? The activity log is dividing the episodes into a set of timestamp activities. Okay, we don't need all this overhead of all the patient history with all the data and this structure. We just need which time, please back. Which time, which patient, which activity, and which activity. We can also include some resources, the hospital or some other elements, but the bare minimum elements in an activity log is which episode, of which patient, which activity, at which time. And this is what is stored in this activity log. This comes from the patient history, and then this is what we use to finally feed the process mining, which is the next slide. So you ingest the activity log. We use to perform this process mining and specifically the process discovery part using an R package called BUPAR. Okay, and once you have when you provide to this package the activity log and state this is the timestamp, those are the activities, and so on and so forth, it provides you a variety of outputs, very interesting to analyze. Okay, what has happened in the reality regarding this cold stroke organization. Okay, so I'm going to show you right now the different outputs we're working with. The first one is the process map. A process map is what we call a directed graph. A directed graph is just a figure where you have these nodes, the balls, okay, which represent activities. Remember, activities, timestamp elements in the caregiving, and edges. Edges are the arrows that link different activities. Okay, that one it is stating that one of the activity precedes another one. The thickness of the arrow could represent in how many of these episodes that have been captured during the episode linking appear this transition, or which is the median time between in this transition. Okay, we'll see clear in the following one, which is a process map with frequency information. So this is an actual process map from the Aragon region linking urgent care data and hospitalization data. Okay, and what is stating this graph is saying to us? So it is stating that usually the cold stroke or the stroke caregiving process starts going to the admission, okay, to the urgent care admission. There has been some cases that it has been directly to the hospital admission. This is pretty strange, but we have discovered that there has been some planned surgeries for previous transient episodes, okay? And this is the reason that in some cases the stroke caregiving process started directly to the hospital. But so you can see that in the thickness of the arrows that usually patients went to urgent care admission, then the first admission in urgent care, there to the observation room, and so on and so forth. Here the numbers express the number of patients that went through between these two activities. Then if you move to the next slide, you can see essentially the same map, but instead of stating the number of patients that go through this arrow between these two activities, is the median time between the two activities related. For example, in median time between the urgent care admission and urgent care first attention was 0.3 hours, which is around 20 minutes. Okay, which is okay. It's a reasonable time. Okay, and also the thickest arrow represents the hours staying in a long stay at hospital, and usually, okay, it's the where you stay the most during this kind of caregiving activities. So next one, the next output and very previous 22. Okay, yeah, thanks. What we have here is, instead of having the overall activities without referring to specific episodes because the process map refers to the whole episodes. What we have here is the specificities of the sequence of activities that has been observed in the different episodes and categorized per episode. So in these traces, what you have is you remove the time component, you just look at the sequence of activities, and what here is sorted by the frequency that the number of patients that went through this type of this sequence of activities. For example, the most common observed path here, so the sequence of activities that occur the most in the episodes observed were starting the emergency room admission, then go through the first attention in red, then go through the observation room, discharge an emergency room, physical exit, because we distinguish between the administrative discharge and physical exit, brown and light blue, then this dark green states hospital admission, and finally the purple is the hospital discharge. And that was observed in the 25.7% of the overall episodes. The second most observed was essentially the same, but in that case, the patients didn't stop at the observation room. Okay, and for example, just to mention, the first trace that have fibrinolysis was this one with 1.6 occurring in 1.64% of the total episodes analyzed. Next output are but we can go quick with them, are the timeline. The timeline is essentially considering in the x-axis the time and the y-axis the different episodes. You can see the dots represent activities, and you can see here, for example, those outliers. Okay, those episodes that have activities that took longer than they expected. In the next slide, you can see essentially the very same presentation, but sorted by duration. So what you can see here is that in the upper part, the shorter episodes, for example, in that case, were the episodes that finish in the urgent care. Okay, this is why it's finishing in this light blue color. Then the big chunk in the middle, which is those episodes related to that consider urgent care plus hospitalizations. Okay, that finish in this purple, and at the bottom, you can see that the ones that include the long stay hospitalization, which are not that acute, but and that were also captured in this process. What you can see here, so you can observe this variability in the duration. Okay, from the very short ones, the variability in the duration of the regular hospitalizations in the middle part, and then you can next slide. So once having seen these outputs, the point right now is what can we do with these outputs? So the first one is the conformance. So trying to answer the first of the questions, which means is the real organization of the health system is the reorganization of the health system following the rules stated in the code stroke guides. So we can do that, for example, to analyze the time to fibrinolysis. Okay, and to do that is very simple. You have this process map with time information. Bupar offers us a fast way to filter the information. So what we do is just cut till the fibrinolysis, go to this node, to this graph, cut until the fibrinolysis, and go to the animation and check which are the time distribution till you reach the fibrinolysis. And what we have observed, these are information from real hospital from Aragon, that the distribution of times was always below 100 minutes, and I guess this is okay with the guidelines, because I guess the guidelines state less than 4 hours. I'm not sure, because that things change, but I guess it's less than 4 hours. You have to take into account that this is only considering urgent care admission. We didn't include the urgent care transportation, okay? But observing these numbers, we can conclude that that the fibrinolysis is given properly, okay? But this is just considering the information with urgent care and hospitalization. We performed that. This is what we call the basic performance. What could be done in a more advanced way? That is what we call the normative conformance. You have to define a graph. You can move in the animation. You define a graph. This is the observed graph. Then you define a graph, the normative graph, which represents what you expect to happen in the reality, and then you compare both graphs. How? Using, for example, graph distance measurements. There are measurements in the literature, okay, and this distance measure will tell you which is the grade of appropriateness from your observed map to the theoretical map you have defined as the normative one. Okay, next slide, please. What did we do also? We computed, or we observed the mortality per trace. Okay, this is the intra-episode mortality. That means intra-hospitalary. That's correct. Mortality. is that the word?
No, in hospital.
In hospital. Thanks. In hospital mortality. Sorry. This is in hospital mortality. Next slide is the 7-day mortality. And the next one is the 30-day mortality, okay? Associated to each of the traces, okay? Well, this is just there is a lot of confusion here, okay? Because we haven't included the specificities of the patients and so on and so forth. The idea is to move next one. Combine, you can go through all the animation. You can combine all the information we have here. So the history, the traces, the time considerations, the organization of the duration of the traces of the episodes, and then perform a survival analysis where you take into account, okay, both the time to the different critical activities, for example, the fibrinolysis or some of the surgeries, etc., and also the traces patients underwent. Okay, so we are right now working on how to perform this analysis. We did some initial analysis, but we are right now working to perform this survival analysis with, for example, using this Cox regression and so on. Next slide, please. And for further work, we are working on the decision mining. Decision mining is even more finer view of the process. And for example, is to check the animation, please. So if you zoom here, for example, you see that in the urgent care first attention, there is these 3 arrows that go outside this node. First, it goes to the discharge. The second one to the fibrinolysis. The third one goes to the observation room. The point is that why a patient went from one of the arrows or not to another. This is the next part of the slide. So, is the proper path. So, what was the decision taken within a node to move through from one arrow or from one node to another, following one arrow or another? Was the proper one? Is the best one? Could we improve the care pathway if we properly define the decisions taken at certain points in the process using this. So those are the kind of questions that should be answered using the decision mining, which is another layer on top of the process. And to finish, I will tell you what have been done. Sorry?
Couple of minutes.
Okay. So what have we've done within the work package 3.3 in the ICTUSnet project. So what we have been doing is doing this kind of analysis in a federated way. So next slide, please. We have the animation. So we have encapsulated these different parts. A little bit more. 3 and 4. Okay. So we have encapsulated in 4 parts the steps of the analysis. There is the source mapping and data extraction, the event linking and activity log generation, the process discovery, and finally the result evaluation. Next slide, please. So you can go through the whole animation. So in a single site analysis, you do all these steps with your data, okay? But what we do in this federation is, next slide, is that at the EACS, let's see how this animation works. What we do is we distribute the log builder and the process mining pipeline, so the parts that are purely analytical. Every single partner in the federation extracts their data and produce their own results, okay, and so on and so forth in the different partners. And then the different partners send these results to us, and what we do is to compare the overall results and provide this benchmark report, okay. And just to finish, what the lessons we have learned from the overall project, the process mining methodology plus these federation elements, is that it's very important to provide a clear data model. Okay, it's very important to have a high data quality. We have been struggling with this. Why I mentioned previously the chronological elements that were full of glitches. It's important to have the high coherence in the time and also a final granularity. The finer granularity, the better the process discovery and the process mining works. And we did some work on that, and it was all covered. All the analysis covered that the outlier analysis, because sometimes it's difficult to define the expected, because sometimes a patient takes a lot of time, and that's in that specific episode was required because some of elements in the caregiving activities. And I think that's the last one. Well, the last one is this animation, but I don't know if that will work. So this is a process map, an animation of the process map, okay, following the patient's path. Okay. It's very nice because it's seeing more than just the static process map.
Mm-hmm.
And that's all by my side.
Thank you very much, Juan. No, it's okay. Actually, we're on time, and we do have. I'm reluctant on getting this out because it's so nice. So, but I should share. I should stop sharing the screen to go to the chat box, because we do have some questions in there. Yeah, the João Vasco Santos is asking whether did you use deterministic or probabilistic linkage?
Well, we can consider this linkage as deterministic, because once you follow all these rules, if the rule system states as the linkage is correct, you consider that these two events to be linked to be part of an episode. So that's a deterministic linkage.
Mm-hmm. Very nice. Ismail actually has posted a couple of questions. Once you construct the process mining map of the clinical process, what kind of results do you discover which cannot be known with other methodologies?
Well, basically, we haven't seen this fine-grained detail for example, in the capturing the traces, or the time the distribution of the distribution of the patients along different across different activities within the care pathway. So, well, I guess this is the fine-grained data. We haven't explored the simulation, but I haven't talked about that. But another possibility is to simulate new cases, so as to check the proper movements of the patients.
Mm-hmm. There is another question by Ismael. Can you compare processes with statistical analysis? I think you have responded. Yeah.
I guess this is the next step, the current step in the survival analysis, right?
And also using the in the conformance, using this centric measures and so on. Yeah.
That.
Okay. So Joe, you've raised your hand. Thank you for joining today. Please pose your question directly.
Thank you, Enrique, and thank you, Juan, for the great presentation. Actually, I think that it would be quite interesting for, using probabilistic linkage, because it might detect and overcome some of the data quality problems that might be related with, and as you stated before, because at the end we know that in sometimes hospitals just do errors in even the times that they are registering. So I think it'd be interesting to and more often is used this kind of approach, and is I think it'll be quite interesting to use and try to see what if the results change with this kind of approach.
Yeah. So I just remember, thanks for pointing that, because within the linkage algorithm, when you check times, there is I did that, but I didn't explore that that part, which I was able to mark suspect linkages. Especially, it was as simple as stating that if a timestamp doesn't have seconds and it finishes at 00 or 05, that could be a suspect linkage, a timestamp that could lead to a inconsistent timestamp or an inconsistent linkage. So I marked them, but I didn't use this information to perform this kind of A/B analysis or comparing the results, taking into account the suspects versus the confirmed or more deterministic ones.
I think it would be also interesting to actually look at both and clearly state what are the differences between them. So if there is changes in times and the main outcomes of this work, because at the end it is quite different to use these approaches, and the results might or might not in this particular case scenario change.
Yeah, and also when if I may, also when linking different data sources, if the objective is looking at the whole universe of individuals passing through the pathway, you need a number of different data sources, and not all data sources have the same ID, so you cannot track down properly. You can use probabilistic linkage also to discover those that are very likely the same people. Yeah, thank you very much, Joe, for raising this point. David Valtar also posed the question: what kind of algorithm do you use? How do you deal with spaghetti processes?
So in that case, I use the process discovery, the basic process discovery algorithm, which is implemented in the BUPAR package, part of which is available in CRAN, part of the R distribution. I don't know if there's the heuristics minor. I cannot remember the name, the specific name of the algorithm implemented there. I think it's the heuristics minor or the prime or the alpha minor. I don't know. And dealing with spaghetti processes. So far, we have up to 9 or 12 different activities, depending on the setting. Sometimes we have CT imaging at different emergency room and hospitalization, surgery, sometimes also in emergency room, some others in the hospitalization. But what I wanted to say that we don't have this huge amount of different activities, and sometimes we don't have these spaghetti processes. And when to avoid what we usually did to avoid the spaghetti processes is working on with the most common kind of traces, the most observed types of episodes. Usually removing those, for example, those episodes that represent less than 1% or 2%, you start cleaning the spaghetti process. That's typical way to analyze, avoiding the very specific, the kind of outlier episodes. So this is what usually we do.
There you go. There is more room, 10 minutes left for this session, and more room for questions, remarks, suggestions. So actually, I'm going to be very brief in the closing. Oh, David Baltar said, so a lot of pre-process work.
Post-process in that case, we would say like that. When you have the spray and post, it's both sides.
I think it's not that miserable as Marta's work on annotation, but it's pretty miserable.
Yeah, but well, as you may know, as part of the data scientist work, the data cleansing, it consumes most of the time. So the effective analysis is just they say that 80-20, 80 cleaning or preparing data and 20 analyzing. So it's the common way of life here.
Any other remark or question you want to raise? So Paco Estupiñán, it's interesting to note that the level of trimming you have to do to get a clear process map is informative on the level of noise or unique rare care secrets there are. And I don't know, I cannot see more. Paco, you want to say something live? Full stop. So actually, this is very informative. You have to dig into it, right, to see what's going on in there. Actually, for example, now we are doing this discovery on the in-hospital pathways that a COVID patient follows since they take the test to the discharge. And the number of Paco, how many traces, how many activities we are now working with, and the level of trimmage you're doing? About 50 activities. In that case, David is quite massive, and you need pre-processing, but while pre-processing, you are actually understanding the processes. And this sort of face validity process that you need to in the end have to get the final spaghetti. Any other point? So then we could maybe move to the final closing session. I think the point is that, and the value, if I may, of this kind of methodologies is not in the fact that we are using breakthrough methodologies to deal with complex questions using real world data, which is the case as well. But the beauty of this is that we are trying to implement this kind of things within the context of the healthcare systems in the different regions in ICTUSnet, which means in the end that science, science data and informatics meet at some point to develop learning health systems. So to allow those health systems to learn out of the data they collect, getting sensible information out of that, using, you know, groundbreaking methodologies to change, yes, to change the way they do intervene, they do implement policies, they do behave in the end. So this is the beauty of this project, using, you know, complex methodologies, complex technological elements in place to get something that the systems that we are working with can use eventually in the future. So this is, to me, the effort. It's not about an academic exercise, although we will be publishing papers in the future for sure, because we are scientists. No, the point is about letting them know, letting health system know how to use this, how to implement this to get value out of the data they do collect. This is my overarching, let's say, wrapping up thought for you all. And in terms of what my boss, the executive director of this institution, wanted to say, this will be my last 2-3 words. She actually wanted to raise that following this path, this reflection that I have just made on linking data science and informatics to let health systems to be smarter and you know, follow continuous learning processes. The Institute for Health Sciences in Aragon is pushing hard on the idea of the implementation of this strategy within the country, but also as part of the development of the European health data space that, as you might know all, is currently taking momentum as part of the, is one of the big policies of the van der Leyen Commission for the next coming 6 years. So the Institute for Health Sciences in Aragon currently is a competent authority for Spain to develop this kind of effort on behalf of the country, and we are participating. You know, we are really involved in that, actually coordinating a couple of the core work packages that are in this joint action TEDAS, which is one of the cornerstones of the European health data space. Yes, moving the principles that we are having testing here in Spain and having testing here in ICTUSnet and other similar projects, cross-European projects, to feed the development of such a European health data space. So my suggestion would be, and these are my words, not my boss words, I would suggest you all to follow closely the developments in Europe around the European health data space, because it's going to be, you know, the way forward to the reuse, the secondary use, reliable, they say, secondary use of real-world data to transform the health systems in Europe in the upcoming years. So thank you very much. Merci beaucoup, obrigado. Gracias a todos y a todas por haber estado esta mañana con nosotros. Espero que el tiempo que le hemos dedicado os haya resultado a todos de alguna utilidad. Hemos estado unas 60 personas aquí con nosotros, y querría dar un saludo muy especial a nuestros colegas de Navarra, María, que acaba de aparecer, a Carmen, detrás de la mascarilla, acaba de aparecer aquí. Creo que está presente también Mar Vallet de Aquas, yo, que habéis visto antes representando a hombre, y Elsa también, de la región norte de Portugal. Hombre, está Rosa, la coordinadora de ICTUSnet, que nos saluda ahora, y no sé si alguno más de nuestros compañeros de ICTUSnet. Muchas gracias a todos también por apoyar estas innovaciones que a veces cuesta apoyar. Claire también nos saluda, Nuria también nos saluda. Nuria es parte del equipo trabajando en comunicación, en Open Evidence. Lo dicho, muchísimas gracias a todos por haber asistido hoy y bueno, no dudéis por favor en contactar con nosotros, cualquiera de los que está aquí en las imágenes ahora, para cualquier cosa que necesitéis. Hasta pronto.
Bye.
Bye.